Throughout history, new materials have driven human progress. From the Stone Age to the Bronze Age, from the Iron Age to the Silicon Age, each leap forward has brought profound changes. Today we stand on the cusp of another revolution, the age of MetaMatter. Imagine a world where materials can heal themselves, adapt to their environment, and even think for themselves. This is the promise of MetaMatter, programmable artificial metals that are poised to reshape our world. For centuries we have been limited by the properties of naturally occurring substances, but MetaMatter throws off those shackles. These are not materials found in nature. Instead, scientists are crafting them atom by atom, molecule by molecule. By manipulating matter at the nanoscale, they are creating substances with unprecedented properties. The key to this revolution is programmability. MetaMatter can be designed to respond to specific stimuli, such as changes in temperature, pressure, or even light. This responsiveness allows them to adapt to their surroundings in ways never before imagined. Imagine a bridge that strengthens itself under stress, or a plane wing that changes shape to optimize flight. The possibilities of MetaMatter are almost limitless. In the coming sections, we will explore the science behind these incredible materials, delve into their potential applications, and consider the challenges and opportunities they present. This is a journey into the future of materials science, a future where the line between the living and the inanimate begins to blur. MetaMatter might sound like science fiction, but the science behind it is very real. At its heart lies the concept of metamaterials, artificial structures engineered at the nanoscale to exhibit extraordinary properties. These structures are so small that they interact with light and other waves in unusual ways, giving metamaterials their unique abilities. One of the most remarkable properties of metamaterials is their ability to manipulate light. By carefully designing the nanoscale structure, scientists can create materials that bend, scatter, or even absorb light in ways that defy conventional optics. This has led to the development of invisibility cloaks, superlenses that can resolve objects smaller than the wavelength of light, and even materials that can slow down or trap light. But the potential of metamaterials goes far beyond optics. By tailoring the structure and composition of these materials, scientists can create substances with exceptional mechanical, thermal, and electrical properties. Imagine a material that is both incredibly strong and incredibly lightweight, or a material that can conduct electricity with zero resistance. Liquid metals represent another exciting avenue in the quest for MetaMatter. These metals, typically alloys of gallium, remain liquid at or near room temperature, giving them unique properties of fluidity and adaptability. Imagine a robot that can flow through tight spaces, or a medical implant that can conform to the shape of the body. By combining the power of metamaterials with the versatility of liquid metals, scientists are creating a new generation of materials that can change their shape, properties, and even their function on demand. This is the true magic of MetaMatter, the ability to program matter itself to do our bidding. The potential applications of MetaMatter are as vast as the imagination itself. From revolutionizing industries to transforming everyday life, these programmable materials hold the key to a future overflowing with possibilities. In the realm of construction, imagine buildings that can adapt to changing weather conditions, self-repairing bridges, and lightweight earthquake-resistant structures. MetaMatter could lead to a new era of sustainable and resilient infrastructure, capable of withstanding the test of time and the forces of nature. The aerospace industry stands to benefit immensely from MetaMatter. Lightweight, high-strength materials could pave the way for more fuel-efficient aircraft and spacecraft, reducing our reliance on fossil fuels and enabling us to explore the cosmos with greater ease. Imagine a spaceship that can morph its shape to optimize its performance during different phases of flight, or a drone that can seamlessly transition from flight to underwater exploration. In the world of electronics, MetaMatter could revolutionize the way we design and manufacture devices. Flexible, self-healing circuits could lead to bendable smartphones, wearable electronics that conform to the body, and even implantable devices that can interact directly with the nervous system. Imagine a world where electronic devices are no longer rigid and fragile, but instead seamlessly integrate into our lives. Medicine is another field ripe for disruption by MetaMatter. biocompatible materials that can adapt to the body could lead to revolutionary new implants, regenerative medicine therapies, and targeted drug delivery systems. Imagine a world where damaged organs can be repaired or replaced with lab-grown tissues, and where diseases can be treated at the cellular level with pinpoint accuracy. While the promise of MetaMatter is vast, the road ahead is not without its challenges. Developing these materials requires overcoming significant technical hurdles, from mastering nanoscale fabrication techniques to designing sophisticated control mechanisms. One of the biggest challenges lies in scaling up production. While scientists have successfully created MetaMatter in laboratory settings, producing these materials on an industrial scale remains a significant hurdle. Overcoming this challenge will require new manufacturing techniques and innovative approaches to materials synthesis. Another challenge lies in developing effective control mechanisms. MetaMatter's ability to change its properties on demand is both its greatest strength and its greatest challenge. Scientists must develop reliable ways to program and control these materials, ensuring that they behave as intended in all circumstances. Ethical and environmental considerations must also be taken into account. As with any powerful new technology, MetaMatter has the potential for both good and ill. It is essential that we consider the ethical implications of these materials, such as their potential for misuse in weapons or surveillance technologies. Furthermore, we must ensure that the production and disposal of MetaMatter does not harm the environment. Despite these challenges, the potential benefits of MetaMatter are too great to ignore. These programmable materials hold the key to solving some of the world's most pressing problems, from climate change to disease. By pursuing this research with both enthusiasm and caution, we can unlock a future where the impossible becomes possible. The journey into the world of MetaMatter has just begun, and the discoveries we make along the way are sure to shape the course of human history.